I have an audio amplifier today. This is from Power Sound, who brought me the powered mixer that I repaired a little while ago. He says he's got more work for me, so that's good. This one, Lynx RS4-2000, full 4-channel amplifier, 4 outputs, yeah. And one would assume 4 inputs and 4 outputs. Yeah, there are the outputs. So I've got the power switched on. It's plugged in, and this just appears to be completely dead. Yeah, nothing lighting up, no fans, no anything really. So we don't really need speakers and an audio signal to test this. First of all, we need to, I think, to switch on. Yeah. So okay, let's open this up and have a look to see what we've got inside it. Well, after removing more screws than was strictly necessary, yeah, and found out it comes off from upside down, I'm finally inside this. Oh, yeah, I'm finally inside this thing. What's this? Cardboard. Cardboard. Is this like a cheapo thing or something? Cardboard. Oh, I like that. They put like a little slot here specifically for getting the cardboard out. Yeah, how about that? So yeah, dust as usual. Fans working. Lots of capacitors. Switch mode power supply. It must be a little switch mode power supply. 5 heat sinks. So 1 for each channel, and then I'm guessing the other one is the power supply, and I'm guessing that's where the problem is with it. Interestingly, I can't actually see anything fastened to the heat sinks. You know what? Oh yeah, okay, so the devices are kind of like, you probably can't see them, they're down under there on the PCB. Yeah, so looks like the heat sink comes off. Okay, so let's get a bit further into this and let's have a look at it. Well, I've got most of the fluff out of it and dust. Yeah. I think now, just by looking at this, we can pretty much see what we've got. So you can see there's like 4 pairs of transistors in here, and I think we can pretty much assume these are drivers and these are the output stages for the 4 amplifier modules. And this one is different. Yeah, it doesn't have the transistors. And again, if you look at the output, these are kind of like all looking the same. 4 sets here, yeah, look basically identical, and then this one's the difference. So this one must be the power supply. And the first thing I'm guessing with this is I've probably got no power since it's dead. There's a fuse down here. So you see that at the front. Yeah. So let's have a quick look to see if the fuse is gone. Yeah. Just get hold of the meter, and the wires are kind of tangled up. There we go. Okay. I'm impressed with that cardboard, by the way. It's one of them things, yeah. Amazing some things you see doing this sort of work. Fuse is good, okay. So if you ain't blowing the fuses. Right. Then I guess the next thing to do is to figure out where we can actually monitor some voltage rails in here to see what we've got. I can see down under here it says like there's 2 diodes there. It says D15 and D16. I'm thinking probably that's the one on the positive voltage rail, one on the negative. I mean, an amplifier will have a plus and minus voltage rail with reference to ground, so you might be able to measure there. I'm going to see if I can actually get this heatsink off this one to see what's underneath. I'm pretty sure this is where we need to be having a look. So I'll get a little bit further inside this and then we can see. Right, with considerable effort and a not inconsiderable amount of dust up my nose, yeah, I've got this thing out. First thing you need to be careful with stuff like this, should have mentioned it straight away. This is a switch mode power supply, by the looks of it to me. And these capacitors are very large, 2200 microfarads, 200 volts. These can hold more than enough charge to kill you, yeah. And it could hold that for quite some time after it's been switched off in this sort of situation where it doesn't power on, yeah. So the first thing we need to do, and I would suggest actually the first thing you should do is leave it an hour or 2 or longer. Yeah, but having got it apart, let's see if there's any voltage in these capacitors. I would imagine these could hold a charge for quite a long time. So these look okay. Yeah, that's all 4 of them. So there's no voltage in there, so that's safe. Right, so the most interesting thing I can see to start off with is the thing that I can't see, and that's a bridge rectifier. And I can see that the power comes in on these 2 terminals here. These are your big capacitors, so obviously these don't have high voltage DC. I can see a couple of filter capacitors they look like here, some filter coils, thermistor to stop rushing power, the fuse is okay, I checked it. So there's a switch mode transformer, but I don't see a bridge rectifier. I mean, it could be 4 individual diodes. There's some chunky looking things here, but I'm not sure that's what they are. Yeah, you see them there. But I don't think they could be 4 diodes. But let's get a heatsink off here and let's have a look to see what's under this one. Yeah, so it looks like it holds on with a couple of bolts down here, and for that matter it might hold on with some more bolts further back. Yeah, maybe these as well. So I need to undo at least some of these and see if I get a heatsink off. Well, just to be sodding typical, I've got a socket set and another kind of screwdriver type socket set, yeah, and none of the sockets fit these things. I've got some of them out with the pliers, but these are really tight. I happen to have a set of these which is like metric spanners and 0.5mm sizes, yeah, and these are actually 5.5mm. So if you haven't got something like this and you're doing this sort of work, I mean, without these, I don't know if I would have got this off. You know, I couldn't buzz them with the pliers. Things now stuck in there. More sodding typical, yeah. Things stuck in the span, yeah, it's out. It's out. Bit of brute force. So let's go for the other one. And I'm hoping that's enough to get this heatsink off here. That's those. Yeah. I mean, these all seem to be like a set of 4 1-fridge amplifier channel, and these all seem to be identical, like symmetrical if you like, and then this was the odd one out, of course. Let's see if we can now. Yeah, something's happening. It's coming loose. It's not come off like, but it's coming loose. It's kind of like glued to the output power devices with heatsink compound. Let me see if I can get this off here. Well, it's mostly loose, and now I've spotted the hidden fixes in here, like some sort of take that off, that'd be useful. Yeah, like some sort of star thing, yeah, the hidden one. So once you take that out, I'm pretty confident now this heatsink will actually come off. Oh, it fell off, yeah. Okay, so one heatsink off quite cleanly. Ah, there's the bridge rectifier. I knew it must be here somewhere. Just clean some more dust off this. Yeah, that's got rid of the dust. So I can assume we're going to have some problem in this section somewhere. Yeah, more devices, all upside down, of course, so you can't actually see what they are. That's helpful. We found the bridge rectifier though. So let's have a quick look with a few resistance checks on this to see if we can just spot anything obvious. Yeah. Okay, so power comes in on 2 terminals here. Yeah. This is a switch. I actually had to take the switch off the out of the front panel to get the PCB out because it was hitting the switch and I was trying to remove it. So I think we can pretty much assume that those go there, that way around. I think they did. Switch is on, so we should have continuity here. Okay. Let's have a look. Yeah. I worried for a moment then it was a switch. I did all this for nothing. Okay, so that's that. So then we should have power coming in on here to. Yeah, that goes to the switch. 11 ohms. Oh, that'll be 11 ohms. Will be the resistance of this thing here, no doubt. This inrush thermistor, yeah. Yeah, 11 ohms. So the idea of this, it starts off at 11 ohms, and as the power comes in, it warms up and it drops down to pretty much 0, yeah. Okay, so that's good. So from there to the switch, 11 ohms, yeah. And this should go to one of the AC inputs on the bridge rectifier. That one, yeah, with 11 ohms. The other side of the bridge rectifier should go to the other power coming in. Yeah, it does. So we've got an AC getting to here, which tells me these were holding a charge, unless the rectifier's open circuit. Now, there's no short across the bridge rectifier, which I wouldn't expect there to be, otherwise a fuse would blow, yeah. Let's check the bridge rectifier. I think it's okay. Let's have a look. So, one of the inputs, yeah. Does it go to here? Yes. Does the other one? Yes. So both inputs with a positive on the inputs should go to one end of the bridge rectifier, and then both inputs with in black, the negative on the bridge rectifier, should go to the other leg. Yeah. Yeah. Do there. 1, 2. Yeah. So we know that's okay, and then from the bridge rectifier we'll go to the main capacitors. So we can flick that over. So the outputs of the bridge rectifier are either end, yeah. Is that the bit? Yeah, either end. So one end obviously goes to capacitor up here. How many capacitors have we got? 4. The capacitors in parallel. This might be hard to tell. Or the 2 lots in series. Where's the other one? Sorry, I'm slightly off. Right, these 2 capacitors are in parallel, there and there, yeah, and both go to this end of the bridge rectifier. Yeah, so the other end of the bridge rectifier probably goes. What rating are these? 200 volt, yeah. So they'll be like 2 of them kind of in series, yeah. So the other end of the bridge rectifier will go to the opposite end of the other 2 capacitors. That one and that one, yeah, that makes sense. And then this end of the will go to, yeah, other capacitor, and they'll be in parallel. There's the other one down here somewhere. Lost it up here somewhere. Yeah. So I'll just put on a bit of paper for you, just so you're clear what we've got here. Yeah. So what we have here is quite simple, really. We've got live neutral coming in. We'll assume the live is the one that goes to the switch, if you wire it the right way around. But seeing as like our pulse going either way, there's no live and neutral really. There's a thermistor, which I think actually the thermistor is in here. Thermistor, then what warms up that's in here, yeah. It has a little symbol like that. Okay. Then we got some filters, capacitors across here, and we got some coils in here, which are effectively all this, like we can see here, which we didn't bother to trace because we just went straight from the input to the bridge rectifier. Yeah, but there'll be basically something like this: coil, capacitor, something like that. Okay. And this is just to stop interference getting back up into the mains wiring, yeah. Okay. And then this goes to the bridge rectifier, which I won't bother to draw with the 4 diodes, but AC, plus, minus coming out, yeah. And then we have the big smoothing capacitors, which are connected like this. Okay, and another one. Okay, and they're connected like that because I just measured them. So that's how it is, yeah. So here we're gonna have like about 300 volts DC, something like that, yeah. And that's going into the switch mode power supply. So that's what we have so far, and all that's okay, yeah. All that we know is okay. So then we have to look at it. These are most likely the switching transistors for this, but there's 4 more here, so I'm not sure. Oh, these are diodes, diode. I can't see the markings on these ones, but I'm pretty sure these will be diodes as well. Let's try to lift them up and let's have a look what they are. Yeah, I can't lift those ones, typical. But they got 2 legs on them, yeah. And these 2 are marked diode. Yeah, okay. Under there, those are also marked diode, yeah. So 4 diodes, and this will be generating the plus and minus voltage rails that the amplifier needs, yeah. These will be the switching transistors for this. Okay, let's have a look to see next. We know there's no shorts on this, so we want to have a look to see what we've got around these switching transistors. The transformer, yeah, let's have a look at that. Okay, so I've marked the positive end of the bridge rectifier, and I know this one's the positive end, by the way, because I'm looking at these big capacitors here, and I'm just going to the positive end of this capacitor, and it actually connects to there, yeah. Oops, sorry, out of range. Yeah, so that goes to the positive end of one of the capacitors, and if I go to the other end of the bridge rectifier and find the other capacitors, eventually I'll find where the negative one goes there, yeah. Okay, oops. So positive end of the capacitor goes to this end of the bridge rectifier. This is positive, yeah. So let's have a look at these transistors. So if we go from the positive end, this should connect somewhere on here, and it goes to the middle pin on this one, which will also be the tab, yeah. That'll be the collector if it is a bipolar transistor. I don't know. Be the drain otherwise if it's a FET, yeah. So that goes to there, and then the negative end will go to somewhere else, probably on the other transistor. No, it doesn't go to there, it's a junction, yeah. Probably goes to this end of this one. Yeah. Okay. So negative end to there, positive end to here, and we'll find that this will be the emitter that will go to the collector of that one. Yeah. I'll show you. Let me show you again. And that's good, that's okay. So what we have here is we have transistor like this, yeah. This is the collector, this is the tab that went to the positive end, yes, that'll be the collector. The emitter of this one went to the collector of the other one, and then the end of that one went to there, yeah. This will be the base. And then the transformer, this is going to be a half bridge, same sort of thing you find in an ATX power supply, I would think. Let me have a look. Maybe. I'm looking for something in particular. I'm not sure if I can see it. If this was a half bridge, we would find that the primary of the switching transformer would connect between here and here, yeah? But it wouldn't connect directly. It'd have a winding as a primary, yeah? And then here, you would have a high voltage capacitor. And I'm just looking now to see if I can see a likely candidate for that capacitor, yeah. And I can see this one here. Yeah, 1 kV, so it's a high voltage capacitor. If I just get the focus, you'll see it there. It's hard to focus on, it's so dark. Yeah, let's find the torch. Now let's try to get the thing into focus, yeah. That's probably just too much glare now. Let's see. Okay, you can't see the markings, but I'll tell you what it is. It's a 0.33 farads, 330 microfarads, 1k volts, yeah. So I'm pretty sure that capacitor, now you can just about see it. I'm pretty sure that capacitor is going to be here, yeah. So we can kind of check this out from the junction of the 2 transistors. So that's basically from I'm guessing the bipolar from the emitter of this one. Yeah, from the emitter of this one to the collector. That's the junction of the two transistors. Yeah. So, there. Yeah. And this should go to this coil. And the coil should go to the capacitor. The capacitor should come back to here. Let's have a look. The capacitor will come back to the junction between the capacitors here. Yeah. Let's have a look. So it's the collector of the bottom one. That's here. Yeah. And I'm saying that this should go to the main transformer, which is over here. I'm on the right side of the transformer. Yeah, there. Okay, put the meter where you can see it. So this goes, in fact you can see it comes up here, yeah, and it goes to the transformer here. Yeah. And then the other end of this transformer, but this transformer looks like just a wire link to the meter, should go to that capacitor. No, it doesn't actually, so it's not quite like I think it might be. Oh, it does. Good, I'm glad it does, that proves I was right. And then the other end of this capacitor should go to the junction between the big electrolytics, if I just find it. Yeah, there. There, yeah. Okay, so that's what we have, and it appears to be okay. Yeah, that all appears to be okay. So we want to have a look to see what these are now and see if these are any good. Yeah. I'll get back to some voltage checks in a bit if I need to, but for now this is going to tell us what we need to know. Yeah. So let's have a look. That's going to be very difficult for you to see. I just bent the transistor up, but let me try to see if I can actually see myself what these are. Yeah. Okay, that's what the device is, G4PC50U. Yeah. So I looked up the datasheet for this, and it's quite an interesting device because this is neither a bipolar transistor or a MOSFET. Yeah, it's an IGBT. IGBT. Sounds something like gay rights to me, that. Anyway, that's what it is, one of them, yeah. And this is the thing. So basically this is the symbol for it, yeah. And it's like a cross between a MOSFET and a bipolar transistor. And it's the equivalent of this circuit, but all in one device, yeah. So it's like having a PNP transistor. Now just draw this right, hold on. Sorry, lost the plot there. I was right. So it's like a PNP transistor like this, yeah. But from the base, you have a N-channel MOSFET, yeah. And that's connected effectively to the collector like so, yeah. And this is the gate. So it has a gate coming in. Yeah. And basically, although this is like the emitter of PNP transistor, this is actually the collector. And although this looks like the collector of PNP transistor, it's actually the emitter, yeah. And that's the equivalent circuit that you see of this IGBT. And you can consider it to be an NPN transistor that takes no base current to switch it on, basically. So you put a voltage on here, there's no current flows, base emitter. So effectively it has no gain like a MOSFET, it just has like an RD on, you know, the resistance drain to source on, yeah. But it's like a bipolar transistor as well. It's just one of these unusual devices, so yeah, that's what it is. But from our point of view, it's not really that important, yeah. We can just consider it to be like a bipolar transistor. Just bear in mind there's actually no base emitter current flowing, yeah. So we're familiarising ourselves now with what we've got here, yeah, we can sort of work this out. After the switch mode transformer, we've got, these are going to be your main smoothing capacitors. I'm sure there'll be 3 on the positive and 3 on the negative supply. That's why you've got 2 sets of diodes, positive and negative supply. And I'm sure there'll be 2 pairs of 3 capacitors, yeah. There's some stuff down here. This is clearly an opto isolator, so this should be familiar to you if you've looked at any power supplies or my other power supply videos. The opto isolators here, so we can pretty much be certain that this lot is involved with controlling, switching these, yeah. Let's have a look under the microscope and let's see what devices we've got here. Then we'll go look for some data sheets, and hopefully once we've found those, we kind of like we'll know everything we need to know to get started with the repair. Here then is the part of the circuit of which we're interested in next. Yeah, so this thing here, I wouldn't be surprised if this is driving the IGBTs. When you see something like this where you have like what effectively one leg isn't there, it's normally because the next pins have got a high voltage on them. I don't know what this device is, but we'll need to look that one up. Yeah, so let's I'll just make a note of this thing. It's TOP 245GN. Yeah, 245GN. Also down here we have a couple of chips. Yeah, IR2110S. Again, I don't know what that is, apart from it we made by International Rectifier, I would have thought. 2110S. And we have another chip which is not quite so easy to read the number, but if I get the torch, you probably see it. Alright, okay. So SGS Thompson, SG3525AP. SG3525AP. That sounds like it might be a pulse width modulator controller. I don't know. I'm guessing there's going to be one down here somewhere. Yeah, sounds like it might be that. Other thing I noticed is this funny looking resistor as it is. Just bent it over, but it's red, black, gold. That could be a low value resistor. Is it marked? Well, no, this says capacitor C206, and this doesn't seem to have any marking. Yeah, let's have a quick look. You can't see the meter, but I'll tell you what it says. Just going to measure the resistance of this thing. I'm expecting it to just be a low resistance. Yeah, it reads practically short circuit. I'm on diode mode. Let me just go to resistance mode. 3.8 ohms. Okay, it reads like a low value resistor, which is kind of what it might be. Yeah. The markings don't seem to match. The red would suggest it's 2 and the 0. That's all I can tell from that. Okay, so let's have a look to see what these chips are around here and see if we can kind of work out what's doing what. Yeah. The first one then is that TOP whatever it was. Let's see what we find out what that is. TOP what is it? 245GN. Okay, PDF or data sheet. Yeah, let's see what this thing actually is. Oh, that's the right data sheet. Yeah, I think this might be some sort of switch mode. It's like a little switch mode power supply. You normally find these kind of like in standby supplies. Okay, that's what it is. Let's just grab I'll just print off what I need here, you know, so basically like, you know, from this little picture, and I'll find the actual pin out and I'll print that off. Yeah. Okay, and this is the other chip, IR2110S, which says it's a low and high side driver. This is the MOSFET driver, or for the IGBTs in this case. Yeah, and I think I'll look up the last chip. I think that TOP blah blah chip is driving this effectively like a pulse width modulator. And we have ho and low. That's like ho low isn't like kind of like an Oriental lady of loose morals. Yeah, it's like high output and low output. Okay, just thought I'd just clarify that. Yeah, and these will be our IGBTs. Yeah, I'm enjoying some of the acronyms in this. I'm sorry, guys. You have to amuse yourselves with sometimes with some things. Yeah, so yeah, that seems to be what this is. So I'm suspecting that's sitting between the TOP thing and the MOSFETs. Unless that TOP 242 isn't doing quite what we think it is. The key to that is going to be having a loop to see what the other chip is. Yeah, so let's have a look at the other chip, which is the SG3525AP, because this sounds like a pulse width modulator to me. SG3525 AP. Okay, datasheet. That's the one. Again, we got all datasheet. Yeah, let's go for this one. Pulse width modulator. Okay. Pulse width modulator. This sounds now like what would be driving that HOLO MOSFETs. Yeah. It's interesting, this. I'll just print off pinouts for this one and for the other one, the driver. Now let's have a look to see what we've got here, because I can't quite just get my head around this circuit at the moment, and then I'll explain to you why. I think we've got something quite interesting here. So I get my head around it. What we seem to have, what we do have, is we have a pulse width modulator, yeah, which is this chip here, okay, and then that is connecting to this thing, yeah, high side and low side MOSFET driver, basically, yeah, driver anyway, which is that thing, which I believe is then driving these two IGBTs, yeah. But we also have this, and this one is in itself a little like self-contained switch mode power supply. So you know it's everything in one. It's the pulse width modulator and the MOSFET all built into one, yeah. Drain source, like here, see, a controller. So that's like its own one, which is that thing. And I would have thought that this is kind of like a standby supply, which is probably always on, or at least maybe a supply that starts up first and then effectively generates the power to start this lot up. I'm thinking that's what this is, but what I don't see is another transformer, you know, like a standby transformer or that sort of thing. But I do see this funny thing here that it doesn't seem to be marked, that kind of reads like a low value resistor, but the markings don't make any particular sense, yeah, for a low value resistor. And I'm wondering now if that is an inductor, and this is kind of forming some sort of buck regulator. It's not a switch mode, it hasn't got like a primary and secondary. I mean, there's no other transformers on this, yeah, there's no other apart from this one, yeah. I don't see another transformer anywhere on here. But knowing what this is, I'm thinking maybe this is kind of working a bit like a buck converter and generating the power for this lot to start this up, or should do. That's the best I can come up with as to what I've got here. Let's go and see if we're lucky, if we're really lucky here, and we can find a schematic. If we can, then that's going to help us. If we can't find a schematic, then we're going to have to go on the basis of the supposition I've just made, even though I can't say I've ever seen one particularly like that before, yeah. But we can kind of say, well, look, there's a 16 volt capacitor here, and there's a 35 volt or whatever this capacitor is here, and we can perhaps start by measuring some voltages here to see if there's any power in this area. And that's the best I can come. But anyway, let's have a look first, and let's see if we can actually find, with a bit of luck, a schematic, yeah. Okay, well, based on that idea then, and this is our chip, yeah, so I've actually got this upside down because it matches the orientation of our chip, yeah, on here. And my guess is this is probably the inductor, and probably this capacitor next to it is the one effectively gets charged up, a bit like a buck regulator, yeah. So we can kind of look at that. The inductor, if that's what it is. So let's get the meter in here so you can see it, yeah. Yeah, there you go. So this inductor, if that's what it is, reads 3.8 ohms, yeah. And from this end goes here, okay, and also here. And if you come down this side, it goes there, yeah. So looking at our little thing, all those pins are all connected to the source of the internal power FET, yeah. the drain, which is here on pin 5, the one that's on its own there with the gap, which I said would be a high voltage pin, that will probably go to the bridge rectifier somewhere. Yeah, that goes to the positive end of the bridge rectifier. Okay, the source goes to this coil, and the other end of the coil I think goes to this capacitor. Okay, I'll have to turn the board upside down to check it, but it kind of makes sense. Probably not very focused very well, but this is the coil. Yeah, I have. Just so you can also see from the coil, yeah. That's the other end, they call the 3.7 ohms, yeah. Okay, and this end of the capacitor, which is the negative end, probably goes back to the the bridge rectifier, whichever end's negative. That one, yeah. The one furthermost in. Okay, so that's what we do have. That's what we have here. So yeah, that's the furthermost in. That's the negative end. This is the positive end here. Yeah. So that's kind of what we have, which we can also now add to our diagram. So we have something like this. Well, in fact, this is what we do have, as much of it as I've just worked out. Positive end of the bridge rectifier, yeah, here. Goes to our chip, yeah, which basically is an oscillator and a MOSFET built into one. So this is our chip. This is pin what number is it? 5, yeah. And effectively inside here is a MOSFET, yeah. And the gate is driven by the pulse width modulator, which is built into this chip, yeah. The source comes back out here, and that's then going to our inductor, and then it's going to a capacitor, electrolytic capacitor, and that's going to ground, hot ground, which basically is back to the negative end of the bridge rectifier, yeah. So that's effectively how that chip is wired. And my guess is this kind of like forms like a kind of buck regulator type thing. I'm not saying it isn't, but it's something like that. And you'll end up with a voltage in this capacitor, which I'm then assuming that the voltage in this capacitor then powers up these chips. So I think the first thing we should check is this capacitor to see if there's any voltage in it. Okay, so let's just check some voltages on this. So I'm going to put it on now with the light bulb in series with this. Let's see if the light bulb comes on and then goes dim. I can switch it to mains power now, it's fine. It's not going to go bang. Oh, there's a little green light on here. That's interesting. 300, yeah, you can't see it. 320 volts across there. Is this actually working? There's a little green light on here which tells me I've got some sort of power, yeah. Let's go to the negative of our bridge rectifier, yeah. Let's go to this inductor we're interested in to see if we have any voltage here. About a 15 volt supply. Well, that tells me I was right about what that actually does. It also tells me I might have power on this amplifier, even though when I switched it on before nothing lit up and nothing happened, yeah. Let's get the front display thing. Obviously this is still draining these capacitors. You can see this thing's taking a long time to discharge these big capacitors. This is why I was telling you these things can be dangerous, yeah. Look, 230 volts in there, yeah. And that's with it switched off, yeah. Okay, let me get the front panel. I've reconnected the little front panel thing. I mean, these green lights say the OK lights. I would have thought they would kind of like light up when there was power on. That was the assumption I made to start off with. I'm hoping that was actually a good decision after all that playing around. But you know, I'm sure we've learnt some interesting stuff. Let's just switch this back on again and see what happens. So they don't light up. This one does, but we never had it powered up with that lid off before. So have we got any voltage on the main supply rails then? I mean, there's nothing happening here. To check that, we need to find some sort of ground. Well, this is marked ground. It says ground by it. And check on these diodes, to see. Nothing. Nothing. Right. It appears then that the standby supply is working and got power into here, but the main supply isn't working. There's a good way to check that actually with an oscilloscope without connecting an oscilloscope to the high voltage side of the circuitry, which is a rather dangerous thing to do, especially for your oscilloscope, yeah, and the thing you're trying to repair, yeah, because your oscilloscope is grounded. If you clip the ground clip to hot ground over here, it's something's going to go bang unless you've got an isolation transformer. Now I have an isolation transformer and this is being powered through one now, but if I show you how to do that sort of thing, somebody's going to make a mistake here. Some people skip through these videos and don't watch the important stuff, and then they'll end up connecting the scope where they shouldn't, yeah. So I'm trying to avoid actually demonstrating how you can do that. Comments on the comment section for that, yeah, I'd be interested to see what you think. So let's get the over to the oscilloscope and let's have a look. Okay, so a good way to check if a switch mode power supply is running without connecting your oscilloscope to the ground over here is just take the oscilloscope probe and hold it next to the transformer like so, yeah. Just hold it by the transformer and it should pick up the high frequency oscillations without actually being connected to it. So we'll switch this on again, so the little green lights come on here, yeah. And let's just do that, yeah. And you can see that basically nothing's really happening, yeah. I mean that's actually like mains frequency. I'm touching that's your mains frequency, yeah. That's a mains frequency hum. So we know as a fact then that the standby supply on this is working, but the main supply isn't. So we need to have a look around these chips now down here. The pulse width modulator is the next one we need to have a look at and see if we can determine if that's actually running or not. I've printed off a slightly better version of the datasheet. It's easier to see which pins which. It's the same datasheet, yeah. Just basically just better. This is a Motorola one, but I'm sure it's just the equivalent to that thing, yeah. And so we can see VCC is 15, which is called VI on here. I'd worked out it was a power input from this thing, yeah. But VCC actually power in, and then 16 is VREF, which it mentions here it's an on-chip 5.1 volts reference, yeah. So it's accurate within 1%, yeah. So the first thing we can check if we've got a dead chip normally is to see if we've got a VREF. If there's no VREF coming out, it's either got no VCC or it's dead, yeah. That's the first thing we can prove. It won't always find a faulty chip, but if there's no VREF, you can say it's faulty. If we've got VREF, it doesn't mean there isn't something else wrong with it, yeah, but it's an indication. I've clipped a lead onto the negative end of the bridge rectifier going to the meter, just make it easier so I haven't got to hold two wires at once with these high voltages around. I don't want to be slipping, yeah. So I'm going to look on pin 16 first, which I believe is this end. Strangely, it's not actually marked, it's normally a dot, but the writing this way up, you would think this was pin 1. That's the best I can go by, yeah. So let's switch it on again and let's have a look to see what happens. So again, the standby light's on. So we're looking for 5 volts on here, yeah. And we do indeed have 5 volts. And this is your VCC coming. If I can just get onto the pin. So just get onto the pin 15. Yeah, 15 volts on there. 15 volts on pin 15. So this chip's got power. The next question is it oscillating, yeah? It says on the datasheet here, oscillator output is on pin 4. Not quite sure that applies to our data thing here, yeah. Yeah, it says it's a clock. I'm going to look on pin 4, and if I just put my voltmeter on, I should see like a low voltage on it. If I don't, then I should. I'll just get the magnifier here. Pin 4. There's some bit of voltage on there. Let's put the meter into frequency mode and let's see if we can see this thing's oscillating, yeah. This is a safe way to do this. Let's have a look. So, pin 4. And we have 21.83. What's that in? kilohertz, yeah. That's got the way out. So it's oscillating, this chip is. The next ones to check then are going to be on the outputs, which is on pins 11 and 14, yeah. So again, looking at this, find the right page of it. Yeah, this one. 11 and 14 drive the output, so I'm going to assume this is going up to the other driver chip, yeah, for the high side and low side MOSFETs. I'll check the voltage on the pins first. Make sure there's no high voltages around here. 9, 10, 11. There's no high voltage there. 9, 10, yeah. Okay, nothing to 12, 13, 14. There's no high voltages there, so I'll put it back into frequency mode. And let's see if we see anything coming out of this. Again, I'll use the magnifier, it makes it easier for me to get onto the pin. That's pin 11. And I'd say there's no output. Yeah. Oh, did we have something there? Have I got a connection problem? No, there's nothing there. Pin 14. So I can have something, for instance, and it goes away. That's strange. Let's look on the screen so I can actually see. I'll make this window bigger, yeah, basically. I can see the meter now, yeah. So, pin 11. 10, then it goes away. Oh, that's just background noise, 10 Hertz, yeah. I thought it's reading 10 Hertz now all the time. That's strange. Meter's now reading 10 Hertz. Let's just reset it, yeah. Oh, interesting. Why is that reading 10 Hertz? I don't know. But it's not reading kilohertz, that was for sure. So I think I can fairly much say that there's no drive coming out of this. 9, 10, 11, 12, 13, 14, 0. Yeah. I think the meter's picking up stray noise from somewhere, to be quite honest. It's reading the hertz mode. 100 hertz, that's like double mains frequency. Doesn't surprise me because I've got the negative end of the meter onto the end of the bridge rectifier, which will give exactly 100 hertz, yeah. Even though the smoothing capacitors are there. Okay, that's interesting. It's quite clear then that we have this chip oscillating. I can see on the oscillator output a frequency 20 odd kilohertz, whatever it was, but there's no outputs. Just referring back to the data sheet for a moment, just have a look at that one moment. So this is the data sheet, and it mentions that this has a shutdown function, yeah. If you look at what it's saying here, it's saying that both these pins 9 and 10, compensation and soft start, have current source pull-ups, so otherwise they are held high normally, yeah. I mean, high being probably like VCC or VREF, which is 5.1 or 15, yeah. And it says either can readily accept a pull-down signal, that means you can ground that pin, yeah, or through a resistor, and you'll turn off the outputs, yeah. So basically, if pins 9 or 10 are low, then you'll get no output, yeah. Then it mentions here about pin 10, which is another way to shut it down, which is apparently improves the ability, yeah. So you activate this by applying a positive signal on P10, yeah, and that positive signal it effectively goes on as it shuts it down, yeah, and starts to discharge the soft start capacitor, which is on pin 8. So I think we need to have a look to see on pin 8 or 9 to see if either of them are low, yeah. And we need to have a look on pin 10 to see if it's high. It's strange that the shutdown here has a bar across the top of it, which would suggest it's active low, but the description says it's active high, yeah. And on the other data sheet, you know, I actually had an ST one and a Motorola one. It shows it's active high on the other one, so I can only take that as being an error, and the description as being right. So we want to look for 8 or 9 being low or 10 being high. So let's go over once again to our board, and let's have a look. Yeah. So I'm on voltage range again. We'll power the thing back up. Power it on. It's powered on. Yeah, it'll standby lights on. So 8 should be high. We'll have some voltage on it. Yeah. And in fact, it doesn't. It's low. Yeah. And 9 is high. So that 8 shouldn't be low if 9 is high. Yeah. And 10 is this low. That's low. So shutdown is low. It's not active. Active high according to the description. This is high. Oops, made me jump with the phone. Yeah. So this one is low, and that doesn't really kind of like match what the data sheet's telling us. Yeah. So according to the data sheet, this is the soft start. Yeah. And you can see there's an internal current source here, 50 microamps, which charges this capacitor. It probably charges it either say to 5 volts, which is a reference 5.1, or to 15, which is VCC. Yeah. And so this should have a voltage on it, and the voltage won't go away effectively if you short this here internally by putting a high signal on shutdown. Yeah. This is obviously active high, because high will turn the transistor on and short that down. But shutdown is 0, so that's not high. Yeah. The other one it mentioned, pin 9, I can't just find where it was, but in the description it says if you put ground on pin 9, it will also shut it down, which is actually this one over here. It's not exactly obvious how, but it didn't have ground on it, it had 6 volts on it. So it appears to me we should have some voltage here. I don't think this is an input. I'm sure in fact this is an output if it goes anywhere. Yeah. But this capacitor, it could be faulty, it could be leaky, could have no capacitance, or possibly there's something wrong with the chip, or possibly there's something else connected to here that we don't know about. Yeah. That's grounding it. But let's see if we can actually find this capacitor. Okay. So this is the area of the circuit. This is pin 8 on our chip, pin 8. Yeah. And there's an electrolytic here which is 22 microfarads. There's a chunky looking SMD capacitor here which could be about 5 or 10. Oh, and it goes to here. So the other end, I'm guessing, goes to ground, to the negative end of the bridge rectifier. Yeah, it does. That's where I'd expect it to go. What's the resistance? 6 kilo ohms. I don't know if that's good or bad. I mean, the current source for this is 50 microamps. Possibly with ohms law I could work that out to see whether that is enough effectively to discharge a 50 microamp source. Yeah. So I'm assuming for me we also read 6 kilo ohms. That's where it goes to. Yeah. I think the next thing to do here probably is to take this capacitor off the board and see if it's leaky. Yeah. If it isn't and the capacitance reads okay, we may as well stick it back on again. I mean, I can probably change it. If that is okay, I think we have to change the chip. The other possibility is there's something else coming in here, some signal. There are some transistors down here that effectively is grounding this point and switching it off. Let's have a look, just out of interest. There's a transistor here. Let's go to it. It does go to it. I'll bet this transistor's turning on. We can check that actually. If we go to the base of this transistor here, if this transistor's turning on, that would, because this is the collector, goes to the capacitor, and I bet the other end goes to the negative end of the bridge rectifier. That's exactly where it goes. So if this transistor's turning on, something here is signalling this to shut down, and then it starts to get more complicated. I'll bet that's what's happening. Let's connect it back up again onto the voltmeter and let's have a look. So I'm on our transistor. I mean, there's obviously some residual charge in the main capacitors. Even with it switched off, I'm seeing some voltage here. Yeah. I'm assuming this should turn off, so this is the base voltage, yeah, so to turn the transistor off this needs to be less than 0.6, ideally it needs to be about 0, yeah. So let's switch the power on and let's see what happens on the base of our transistor. Okay, that's off. 4 point, oh yes, and then it goes on when I switch the power off to shut it down. Oh, that's about right. So when I switch the mains power off, that goes high. When I switch the mains power back on, that goes low. Okay, that's actually normal, yeah. So when I switch the mains power off, that shuts down this instantly, yeah. That makes sense. Okay, so let's have a look at this capacitor. So we can see there's no volts on here. We'll take this capacitor off and see if that's leaky. If it isn't, then we're going to have to order a chip. Okay, so I've got the capacitor off the board. Yeah, came off quite easily actually. You can't see it's under there. Yeah. But on resistance, this is reading no, I think it's just charging up. Let's have a look. I mean, that should eventually just go to open, yeah, as the capacitor charges. I mean, it's a very high resistance it's reading now anyway, but I'm expecting this will just charge up. Okay. Should effectively go open circuit. I mean, that's the whole point of a capacitor, yeah. It's taken a while though. That's a bit surprising that for a capacitor on my resistance meter. Let me get another 5 microfarad or 4.7 microfarad and do the same, yeah. So obviously, yeah, it's got charge in it, yeah. And now connected the other way around. Let me just try another, like, electrolytic. Okay, yeah, I've just got a 4.7 microfarad electrolytic. I mean, why not, you know? So let's just stick on the negative. I mean, normally this just reads like open. Yeah. No, it does. It shows it charging. Alright. That's fair enough. I'll stick the electrolytic on here anyway. There's no harm. I can soon tag this onto the board just temporarily to test it. Yeah, so 25 volts should be fine. Stick this on here. I'm just going to tag it on and test it. If it makes no difference, I'm going to order a chip. Because the transistor switching on that pin, everything seems right, all the other pins seem right, so I'm going to order a chip and see if that's it. Just give me a moment while I just stick this onto the board. There's our electrolytic just fastened on the board. The negative end is connecting to the negative end of the bridge rectifier, so it's the right way round, yeah. So let's just see if that made any difference. I don't think it will, because I think all the capacitor was okay. No. The light bulb came on with current limiter for instance, but that's about it. No, that has done something different. Oh, one moment. While I was doing the soldering, I actually disconnected the power lead. Seemed like a sensible thing to do, yeah, for safety, so I've actually unplugged it. So let's just try it now and see what it actually does. Okay, standby's on. Still no lights on here, yeah, you can't see it. Still no lights on the little front display panel. Zoom out a little bit, you'll see it. There you go. Still no lights on the front display. You can probably see the oscilloscope from here, just half behind the microscope, which is good enough, yeah. Let's just get the lead, but I'm sure this is not running. Okay, let's just stick this near to the transformer. No, nothing. Okay, guys. I think that's as far as we can go with that one at the moment. I need to quote the guy anyway, so I'm going to come back with him again for a quote on this one. And order the chip if he wants me to do that. Yeah, still switch it on at the moment. Switch it off. Order the chip. I mean, we've traced the way that part of the circuit's working, yeah. Our other capacitor didn't help. The transistor that kind of switches that effectively when you turn the power off, that seems correct to me. I can't see any other reason why there would be a low voltage on that capacitor unless there's a problem with the chip. Okay, so in the absence of a schematic, I'll ask around as well. I'll see. In fact, hopefully, maybe some of you watching this might have a schematic for this as well. Okay, so I hope we've all learnt something, and this one's obviously going to be a part 2 unless the guy doesn't accept the quote. In which case, well, we gave it our best shot, yeah. Alright, see you soon in the next one, guys, and hope you enjoyed that one.